please.
Thank you. So let me start by thanking you first for organizing this conference and putting together this beautiful meeting. Yeah, this is roughly the topic, but it was called a lecture, so I'll take the freedom to advertise a little bit higher structures and give an introduction to higher structures. It probably will be too elementary for some in the audience, so it's okay if you're not off, but I thought, well, everybody, or some people are still jet-lagged, so it's okay to start easy, right? A few collaborators of mine, Martin will give a talk later that is very closely related, and also credit to John Bias and Urs Schreiber, they explained the stuff mostly to me via lecture notes and so on. Okay, so outline of the talk, as I said, I'll first talk a little bit about what are higher structures and why should you care, so I shamelessly advertise these mathematical notions and why they're cool and why you should work on them. I give the example of higher structure that everybody should probably learn first. That's the most important, even if you do quantum field theories or classical field theories, they appear there. Talk a little bit about high gauge theory, and then I come to this topic, high gauge theory and superconformal field theories and the M5 brains, right? So then come to our attempt so far. I should say that this is work that this is still at the beginning, so I don't claim anymore that this is an M5 brain model or anything like this. So we are still at the beginning, but we do have six-dimensional, at least at a classical level, six-dimensional superconformal field theories that avoid some of the no-go theorems. And then I perform the reality check, show you what's going wrong, what we still have to fill in to get what we want to get, if it's possible, right? Okay, so what are higher structures? The first thing you need to know about higher structures is that we have to start with category theory, and I have this beautiful quote from '89. It's very famous, and this is the one that I like very much because it pretty much describes, I got sucked into this topic by trying to study higher structures and five brains and so on, and then you fall in love with these higher categorical structures, and so you use more and more of them and you can't get rid of them anymore. Okay, so categories, everybody knows that, right? So the observation is just that mathematical objects automatically come with corresponding maps, and you should combine them somehow, and this entity that combines both of them is called a category. So vector space linear maps from the category of vector space groups, group homomorphisms, and so on, right? This is what everybody is familiar with, and it makes sense to combine them. So what do you want of them? Well, you have a class or set of objects, you have a class or set of maps and morphisms, and I'll always denote it in this manner, right? That I have C1, the maps with a double arrow, C0 are the objects, and what this double arrow is simply if you have a morphism, then it has a source and a target, right? So this is what this indicates. You can compose morphisms, this composition is associative, and for every object you have an identity morphism, right? So you don't need to know too much about this stuff. This is roughly what you need to have in mind if you haven't seen them before. So categories give us a meta language. Somehow they extract the essence of mathematical structures, and this is very important if you want to generalize mathematical notions, as I'll explain later. But there's also something else to category theory, and John Bias always stresses this, that it gives you more freedom than sets, because in set theory, you have these objects, and either the objects are the same or they're different. But category theory now gives you more freedom if you work with categories. Namely, you have two objects, and you can't just ask whether they're the same or whether they're different, but you can ask whether there's a relating morphism between them, and whether there's a relating morphism in the other direction, whether you have relating isomorphisms or something like this, right? So you can ask more questions, right? However, now we just postpone this problem, then we can ask whether two things are equal or different to the level of morphisms, right? Because now we don't have anything between morphisms, so we can just ask, are two morphisms the same or are they different? So how can we solve that? Well, we just go to two categories where we have now morphisms between morphisms, right? So effectively what happened is that our morphisms are now no longer a set, but they form a category themselves, right? And this can be iterated, obviously, so you can have morphisms between morphisms, and so on. And then you get to infinity categories where you have general n morphisms, right? So that might be enough about higher categories. So where would you need them? Well, there are a couple of examples where you would be interested in them. Let's look at the first one where you have 2 points on a torus. There we have two morphisms, which is essentially a path from one point to the other. And there's another one that winds once around it. And now you can ask, okay, can I homotopically deform one path into another? Is there continuous deformation of one path into another? And this gives you this little two morphism, right? So this one can be deformed into this one. However, the one that winds around, I can't deform this one around that one, right? So there's no two morphism between them. Another example that I find quite nice, and I've been looking into that recently with project students because it's a nice source of projects for bachelor students, is that there's also something in computer science or in proof theory where you say, okay, I have a bunch of assumptions, and I have a statement in forms of a theorem, and then morphisms are essentially the proofs right? So you can have a proof 1, which is a morphism. You can have proof 2, which is a morphism. And then you can ask, are the proofs somehow related? Can I somehow deform one proof into the other? And this gives you then a 2 morphism, right? And this is indeed how you can formalize proofs in proof assistance and so on, which is quite interesting. And last example is essentially what motivates this from string theory perspective a little bit, right? So you have here endpoints of strings. You can think of these as D-branes. The strings themselves would be morphisms. And then a parallel transport of strings would be a 2 morphism mapping one string to the other, right? And because you have arrows all over the place, there's this nice cute quote by Steve Avodi. Okay, so what about higher structures? How does that work? Well, in mathematical structure, Bourbaki style consists of 3 components, namely you have a bunch of sets, you have a bunch of structure functions, and you have a bunch of structure equations. Okay, and this defines, so for each mathematical notion, group, Lie algebras, vector space, whatever you like, principal bundles, you can always group them in these 3 groups, right? And then the categorification is the following. You roughly replace the set by categories, the structure functions by structure functors, structure equations by structure isomorphisms, right? That's it. So as an example, you can look at a group. From group to go to a 2 group. What do? Well, what's a group? It's a set, has certain maps and certain relations. So the set is mapped to category. The product identity and the inverse is mapped to functors. Here I should stress that you should think of the identity element in the group as a preferred map from the one element set into the group G itself. Associativity in the group is lifted to an isomorphism, to structure isomorphism. So you have an associator that encodes how you get from one expression to the other one. They're no longer equal, but they're now related by a morphism, right? And so you have unitors, and you have also the inverse is also lifted up to that the inverse element times the original element is just isomorphic to the identity. This process is not unique. You can fix various of them. You can ask, for example, that the associator and the unitors are strict, so that they are satisfied on the nodes that they're trivial. And then you get strict 2 groups and so on. So that's not quite unique, but essentially you have a reasonably well-defined definition or notion of how to go from ordinary mathematical objects to higher structures. Okay? So the next question is, why should you care, of course, about these things, right? There's a lot of mathematics that you can learn behind this. Well, essentially 2 reasons. First of all, you're already using them if you're doing string theory. And the second one, because it's technically nice, right? Before we were really living in caves, in a sense. Okay, so let me give you a couple of examples and show you why we're already using them in string theory and why they're there anyway. So first thing is, probably the very basic step, is that the step from point particles to strings means that you go from a manifold, where we had all point particles, they were just points on our manifolds, we now go to loop space of the manifold. And now there's a very clear correspondence between certain bundles over loop space and higher bundles over the manifold M itself. So there's a process called transgression that takes U1 bundles over the loop space to U1 gerbs over the manifold, which is a categorified bundle. And if you put a string structure on loop space, then you get, if you put a spin bundle over loop space, then it gets what's called a string structure over the manifold. And that will indeed be the basis for the gauge structure that we'll use later on in our constructions. On the other hand, you know that we have lots of higher form fields around. They should be thought globally as connections on higher bundles. So locally, of course, you can just think of them as higher gauge potentials, and you can construct curvatures and so on. However, if you want to glue things together globally, you better think of them as connections in high bundles, otherwise things go wrong. In particular, the Kalb-Roman B field, this has been known for a long time, that's a connective structure on a gerb, and so on. The higher forms coupling to DB branes, you get then higher gerbs. T-duality, next point, also generalized geometry if you're a mathematician. Behind T-duality and in particular generalized geometry are these Courant algebroids. That's a nice way of describing the infinitesimal symmetries that are behind that. And Courant algebroids are nothing but symplectic higher Lie algebroids, so we have higher structures there. Double exceptional field theories, if you look at the corresponding structure behind them, you get a slight generalization of Courant algebroids, so also higher symplectic generalizations of Lie algebroids. Then you know that there is, in T-duality suggests that you should not just work with manifolds, but also with generalized notions of manifolds like orbifolds and so on. They are in fact stacks, so they belong to bi-category, also high structures there. And then there's string field theory, right? So string field theory, closed string field theory has been known since the work of Zwiebach in '92. That's based on higher Lie algebras, namely L-infinity algebras, and we'll come back to that very soon. And open string field theory is based on higher associative algebras. That's A-infinity algebras, an analog of that. Well, if you just do bosonic open string field theory, you can use Witten's transdiamonds like formulation of open string field theory. However, if you want to supersymmetrize it, then you get singularities and you really need to switch to A-infinity algebra. So there's also higher structures there, right, from ground up. Then to zero theory, one theories, and F theory, I claim they should be high gauge theories. If they're high gauge theories at classical level, that's a different question, but at least morally speaking, there should be high gauge theories. So we have plenty of reasons within string theory to, well, higher structures are already there. But you might say, well, I don't believe in string theory, that's fine. Let's go to supergravity. Higher form fields are there, so we need higher bundles. Then there's tensor hierarchies and gauge supergravity. They're effectively high gauge theories, right? They're just high gauge theories in disguise in the construction. Okay, then you might say supersymmetry, I don't believe it. LHC hasn't found any evidence, so let's throw that out of the window. Well, we still have field theory. Then there's the abstract definition of topological quantum field theories. They use high categories of cobordisms. That's very mathematical, so let's go to something more physical. It's AKZ constructions based on symplectic higher Lie algebroids, also still quite abstract. Something that everybody needs to know who quantizes gauge theory or should know is at least Beer's TBV formalism. And at a classical level, the statement is the following, that any classical field theory actually gives rise to a higher Lie algebra, or more specifically to an L-infinity algebra, which completely encodes the structure of this classical theory. It encodes the symmetries, the fields, the observables, Noether identities, and so on, right? So that's all there in this L-infinity algebra. And classical equivalence of field theory corresponds to a well-defined notion of equivalence of L-infinity algebra, so quasi-isomorphisms, if you know that. And on the other hand, any quantum field theory yields a loop or quantum L-infinity algebra, right? So there are, even if you do ordinary quantum field theory, L-infinity algebras are already there, and they're quite helpful, should be quite helpful. And then, of course, if you study moduli spaces to gauge field equations, you get stacks. We saw that they belong to bicategories before. Okay, final reasons, quantum gravity, if you like non-commutative geometries, deformations of space-time, then a non-commutative geometry should probably be only the first approximation to a quantum structure of space-time. There should also be non-associative spaces. We see first indications of that in string theory, and ultimately we want that the algebra of smooth or analytic functions, whatever you prefer there, of your manifold should actually be replaced by some A-infinity algebra, which is the most generalization that you can imagine. I mean, this seems at least like a sensible limit currently. This is already visible in string theory, namely if you have D1 branes ending on D3 branes or DP branes ending on DP plus 2 branes. The model for monopoles, for example, in string theory, then you get this fuzzy funnel. So the D1 branes opens up on the D3 branes. They have to gain two spatial directions, and they do that by each point polarizing into fuzzy two-sphere. So here this is okay. This is an ordinary geometric quantized two-sphere. However, if you go to M theory, this configuration lifts to M2 branes ending on M5 branes. And there actually you need a geometric quantization of S3, which nobody has fully developed actually at the moment, because this is just a higher quantization, right? You quantize, instead of a pre-quantum line bundle here, you have a pre-quantum gerb, and they're hard to get under control. But we know that there's a notion of higher geometric quantization behind that, okay? So higher structures are really everywhere, all over the place in our things. Let me give you one more motivation, namely it is actually quite useful to study them. Namely, if you want to generalize or deform mathematical structures that you're interested in, right? So category theory, as I pointed out before, it extracts essentially the essence of mathematical objects. So if you want to generalize something, it's of course helpful to know what the essence really is. And it gives you a hint of what mathematically consistent generalizations should be, right? It makes them kind of obvious. It's kind of a recipe how to generalize things in certain ways. Let me give you a quick example that I found very beautiful when I learned myself what I mean. So let's look at principal fiber bundles, so the structure behind the kinematical data of gauge theory. And just as the principal bundles themselves without connection, just in terms of transition functions, so you can nicely calculate with them as a physicist. So what do we have? Well, we have a group G, and we can see this group as a category with one object and G worth of morphisms. So every element in G corresponds to morphism. Composition of morphisms, just group multiplication, right? So this is standard construction. Then we can choose a cover of our manifold. And this cover itself also yields a category, namely the following category. So objects are just points on the manifold on a cover, right? And morphisms are just the intersections of these covers. So this is X on UB, X on UA, and the morphism between them is X on UAB, right? So, and then you can compose them, you can even invert them. This actually forms a groupoid. But we do have a category, right? And now the principal idea behind category theory is that objects are not important, but we should actually look at the morphisms. Everything that's good and interesting should be a morphism. So let's try to construct a morphism from here, from this category to this category. So it's a functor from this category to this one. What do we get? On patches, we have to map into the one single element set. So this is a trivial map. However, on the morphism, on the double overlaps, we get a map into the group. So we get GIB. And together with the fact that functors respect composition, we get the usual co-cycle condition for principal bundles. Natural transformations automatically give you the co-boundaries, or natural isomorphisms, I should say, give you the co-boundaries between these. And now it's very, very obvious how you generalize principal bundles, right? I mean, this picture is completely trivial to generalize. You just put here something more general, you put here something more general. If you want higher bundles, you replace this group here with a two group, or the corresponding category for two group, or three group, or infinity group if you want. You can also put something down here, then you get what's called a Lie groupoid, and then you just get the data for gauge sigma models, for example, right? On the other hand, you can also replace this here by something else. So if you don't like the notion of an ordinary manifold, but you want a categorified space, for example, then you just replace this appropriately, and then you get the corresponding bundles there. So this definition automatically tells you how to generalize this notion, how to categorify them appropriately, right? And higher structures are very useful for that. Okay, so if you can't escape them, we might as well learn this stuff, and it's actually very beautiful mathematics. It's very easy to get sucked into this. Okay, so as an example, let me show you L-infinity algebras, L-infinity algebroids. Apologies to everybody who's seen that before or knows that inside out by now. I think the easiest way to define them, and which is very physicist-friendly, is probably via NQ manifolds. So let's first remind you what these are. So an N-manifold is just an N0 graded manifold with coordinates of degree 0, 1, 2, and so on. Think of it as a manifold, and on top we have a graded vector bundle, and as graded subspaces of degree 1, degree 2, and so on. So here, these fibers are parameterized by coordinates of degree 1, of degree 2, and so on. That's an N-manifold, and becomes an NQ manifold if we add a homological vector field or vector field Q of degree 1, which squares to 0. Right? So that's a very simple picture, right? A graded bundle with some vector field on it. And physicists, of course, should think of these degrees as ghost numbers, Q as a BRST charge, and it's very familiar from BST quantization and string field theory. Important from a mathematical perspective is that the functions on this manifold, so on the total space of this graded bundle, together with Q form a differential graded algebra, which is also known as Chevalier-Eilenberg algebra of the corresponding L-infinity algebroids. So first example, we can look at the tangent algebroid. So you just take the tangent bundle of your manifold, and this 1 just indicates that we shift our coordinate function by 1 in degree. So the coordinate functions get shifted. That means locally I have coordinate function x mu on the base and psi mu of degree 1 in the fiber. And because they're of degree 1, they anti-commute, and then it's not hard to see that functions on these two coordinates can be directly translated into functions on x mu and dx mu. So effectively what you get are differential forms. Moreover, the canonical Q that you have there is psi mu contracted with d by dx mu, and this of course translates into the de Rham differential. So you directly recover the de Rham complex, which is very important because it's also one important ingredient in the description of kinematical data of gauge theory locally, at least. We need differential forms, right? So it's very easy in terms of these NQ manifolds. Okay, let's look at more interesting examples, right? Remember, we have this graded bundle and Q, which squares to 0. Let's look at Lie algebra G, and we shift it in degree by 1. So now we have these coordinates psi, which have degree 1, and we need this vector field Q that has also degree 1. Okay, so let's construct it. I have only these coordinate functions, so I better derive with respect to them. Now this is an object of degree -1 because it takes away something of degree 1. So to get it to degree 1 altogether, I have to multiply it by 2 factors of psi. Each has degree 1, right? So that's the most general thing I can do. Multiply by constants, so linear combine all of these, and the factor for convenience. And now Q squared equals 0 is precisely the Jacobi identity for these structure constants. So these are really the structure constants of my Lie algebra. So also Lie algebra, the second important ingredient in gauge theory, is described in terms of these NQ manifolds. And now you can generalize that. You can ask, why should I only have something in degree 1? Why don't I have something in other degrees as well? Well, okay, let's do that. So let's say our base manifold is just 1 point, right? And then we just have a graded vector space on top of it. And then we get n-term L-infinity algebras or Lie n algebras. They're indeed equivalent to the categorification of a Lie algebra, at least for n equals 2. This has been proved. For higher n, it's expected. It's just a technicality, I think. If you replace the point by a general manifold, so you don't have a vector space but a vector bundle, then you get a Lie n-algebroid. Okay, so that's a very, very easy definition of higher structures, right? I mean, you just have graded vector spaces or graded vector bundles and some vector field. And you already have a very, very useful concept of L-infinity algebras. Something else that you can do, which is very important, is that you can put a symplectic structure on these NQ manifolds. It should be compatible with Q in the sense that Q is a symplectomorphism, or is an infinitesimal symplectomorphism. And then what do you get? Well, if omega is of degree 0, you get a symplectic. Yeah? Sure.
I'm used to thinking of L-infinity algebras that the Jacobi identity isn't obeying the.
Yes.
It's only obeying the homotype.
Yes.
So I guess I'm too ignorant, but I don't see how your definition there encodes that. Where is the Jacobiator?
So if you
below the next
here.
Yeah.
In this, I'll show you the example of Lie2 algebra on the next slide. Then you'll see it probably, right? Okay. So then we have this hierarchy that is relevant for double field theory and T-duality for description there. For us, more important is that if you put a symplectic structure on Lie n algebra, then this corresponds to introducing a metric. So a metric on a Lie algebra corresponds to symplectic form on this NQ manifold encoding your Lie n algebra. And we'll need that later on for our actions. So there's a big story behind higher categories and differential graded structures. If you want to learn more about this, Urs is very good at explaining that and knows all about it. Hisham as well. There's quite a few people who know the story. Okay, so here's the Lie2 algebra. I'll go through this example in detail, then you might see it. Okay, Lie2 algebra means we have now two non-trivial components of our graded vector space, something in degree 1 and something in degree 2. And let's construct it. Let's go through this example explicitly because it's the first high example and interesting. So we have coordinates of degree 1 on W, V of degree 2 on V2. And now we construct just the most general vector field Q of degree 1 that you can imagine. So first, derivative with respect to W. So this is a -1 degree object. So to get something of degree 1, I should better multiply it by something of degree 2. And V is a is a candidate for that. V is a coordinate of degree 2, so this fits. Okay, a structure constant before to linearly combine these terms, done. Then I have another other possibility, namely I can combine d by dw with two factors of w, which are both of degree 1. Right? So you get again something of degree 2 in front of something of degree -1, degree 1 altogether, structure constant in front of it, done. Then I can have a derivative with respect to v. Then I need, this is of degree -2, so I need something of degree 3 to match it, multiplied by w and v, structure constants, done. And the other alternative that I have is d by dv together with 3 elements of degree 1. And this is indeed the most general vector field Q of degree 1 that I can write down as it stands, okay? And now if I take the square of this vector field, now I don't just get the Jacobi identity, I really get Jacobi identity up to other terms, right? Because now all these terms can mix and they give you precisely these other terms that you want. So if I have 2 terms of these, which correspond to the usual Jacobi identity, I can also produce that by 1 term of this type and 1 term of this type, right? And this is exactly the Jacobiator then that you get, all right? So this induces this Q just as we had before, right? I mean, we had here this structure constants of a Lie algebra. So now the prefactors are more general and we have different types. So they induce higher brackets or products of this form. We have a unary product just from this constant. We have binary ones from here, and we got a ternary one from over here, right? And Q squared equals 0 doesn't correspond to the ordinary Jacobi identity now, but it corresponds to the homotopy Jacobi identity. And it tells you exactly what you expect. So mu1 should just be a differential, so it squares to 0. It should be compatible with mu2 in the obvious sense. And the Jacobi identity is now no longer satisfied, but it is violated, but it's violated in a controlled way, so we know exactly how it's violated, right? And that's the point, right? I mean, this is the spirit of categorification, right? That the structure relations hold only up to isomorphism. So things are violated, but violated in a controlled way. We know what happens. And then it's not too hard to generalize that to 3, 4, 5 infinity algebras, right? You just switch on here more terms. So everybody knows now how to define these higher Lie algebras. Okay, L-infinity algebras. I remind you again, so we have Lie algebra in bracket picture, a vector space, antisymmetric by linear product, like this, and they satisfy the Jacobi identity. The L-infinity algebra in bracket picture, we have this graded vector space that formed essentially the graded vector space of the NQ manifold that we had before. And then from the Q, we get these graded antisymmetric multilinear products, mu, they're of degree 2 minus I, sorry, and they satisfy this higher homotopy-Jacobi identity. Don't worry about the signs, there's a well-defined procedure how to associate the signs. Roughly what they are is they're just, you can sum them up and then you get the dual of the homological vector field Q. Okay, so now an important thing is, and this is something new that happens in L-infinity algebras over Lie algebras, is the structure of morphisms there, and you get something else, and let me stress this here, because that will be an important mathematical consistency checks in all the constructions of high gauge theory and so on. So the morphisms of NQ manifolds are now in principle clear because they're just graded manifolds. You know how to describe morphisms of graded manifolds. That's nothing particularly spectacular. So you have morphism from graded manifolds. And because they carry this vector field Q, you want that it's compatible with these morphisms, right? So you want that the pullback essentially satisfies this relation. So pullback of the functions on one satisfies this relation, commutes with the Q. Morphisms of L-infinity algebras are then derived from that because it's just a dual picture, right? So you can, there's a straightforward way in which these morphisms give rise to these. And then you get these maps phi I, and they're multilinear maps that take I antisymmetric powers of your L-infinity algebra and map to the target L-infinity algebra. You have phi 1, which is just a chain map of complexes, and you have phi I higher i's that link essentially the higher products between these. Okay, don't worry too much about these details. The important thing is now this new aspect that you have here, not only isomorphisms, which would just be maps phi, where phi 1, this chain map, is invertible, but you also have quasi-isomorphism. Right? And this means that phi is a morphism, just any morphism, but that phi 1, which can be restricted to the cohomology, is actually induces an isomorphism. Okay? So the important message here is for Lie algebras, we just have isomorphisms, and quasi-isomorphisms are isomorphisms. For L-infinity algebra, there's this new notion of quasi-isomorphisms. And now L-infinity algebras, they don't have to be the same size, but you should still consider them equivalent. And the important thing is that all our constructions, in particular constructions of physical models, should be agnostic about quasi-isomorphisms. They shouldn't care which quasi-isomorphic L-infinity algebra you choose. They should just work for all of them, right? And this will be an important consistency check. So as an example, let's look at a Lie2 algebra that looks like this. So you have something G, an identity morphism to G. Now here you see that here everything is a co-boundary because everything is in the image here. And here nothing is in the kernel. Kernel is trivial. So as an L-infinity algebra, this is trivial to the trivial L-infinity algebra, just zero-dimensional vector spaces everywhere. On the other hand, and this is a very, very interesting one that's also used later, if you have a Lie algebra and you just enlarge it trivially to an Lie2 algebra by putting in zero-dimensional vector space there, then this is categorically isomorphic to the based paths and the based loops. And the reason for this is simply because if you take two based paths that have the same endpoint, the difference of them is just a loop, and the difference therefore is in the image of this E map, of this embedding map of the based paths, based loops into the based paths, and therefore the cohomology of both of them is the same. Okay, so now let's come to higher gauge theory. And the reason why I presented so much of this categorical stuff is really because this is actually true. So category theory gives you the way of defining these higher bundles, defining all the higher notions that you need, and you have definitions are left as exercises, essentially. You sometimes have to work very hard to tease out all the details, but this is just because category theory is very powerful and combines a lot of things in it. Okay, so the first step is to construct the kinematical data of a gauge theory. And we first should encode the kinematical content of a gauge theory in a very nice, transparent way that allows for categorification. Okay, so what do we need? Well, we need a gauge group. This will be replaced by a higher gauge group. In principle, we know how to construct that, right? So there's a few details, but that's in principle straightforward. We need a principal bundle. Well, that we replaced by a higher principal bundle. I showed you how this can be done in principle. Not all the details, but in principle, we know how this works. And then we need a connection, and this is what we want now to describe. Because we know the global stuff roughly, let's focus on the local stuff, because that's good enough for the purposes of the rest of the talk. So local connections are Lie algebra value differential forms. Now the problem of this is that we have two different things that we want to somehow mesh together. We have Lie algebras and we have differential forms. But just as we don't compare apples with pears, but we shouldn't compare these two, put them together. I should lift it up into category fruits or something like this, right? And then we can suddenly merge these two, right? So how do we do that? Well, there is a unifying category, a unifying mathematical language, which is just use functions on NQ manifolds, right? I showed you that functions on NQ manifolds can give differential forms. And we saw that we can encode Lie algebras as NQ manifolds. Okay, and then we have, this is the one that encoded our differential forms, T1 of M. And Lie algebra is just replaced by this Lie algebra that I showed you, where I just grade shifted the vector space by 1 and introduced Q encoding the structure functions. So in reply to this quote that poetry is the art of giving different names to the same thing, Henri Poincaré coined this phrase that mathematics is exactly the opposite thing, giving the same name to the different things, right? So here we have different things, and we gave it the same name, namely it's NQ manifolds. Okay, so first attempt, inspiration from category theory, everything should be a morphism. Okay, so let's try that. What can we do? Well, we have here our Lie algebra. We take the functions on that to get our differential graded algebra. Remember, the functions on an NQ manifold give you a differential graded algebra. And we map it into the differential graded algebra of forms, described also by an NQ manifold, right? So this is a nice morphism of NQ manifold. And let's see what we get, right? So here we have a coordinate of degree 1. And once we fix the morphism on the coordinate, because all other functions, they are polynomial here, are then automatically fixed, right? If I know how to map a coordinate to something else, I know how to map polynomials to something else. So because the product has to be respected. So this coordinate is now mapped into an object of degree 1 on RD. Well, and this object of degree 1, which has a Lie algebra index, what can it be? Well, it's actually the gauge potential, okay? So that's a good thing. So we get the gauge potential out. And now this morphism has to respect the Q, right? The Q here was the Q that encoded the structure constant. The Q here is the de Rham differential. And compatibility with this demands the following. Q on psi alpha is this one, that was the Lie algebra side. On the other hand, this should be the same as D of A alpha. And if I apply the morphism, this morphism to this object, then I get this part. And so I get the equation dA is just the commutator on half the commutator of A wedge A. Equivalently, I get this equation, so I get the gauge potential is flat. Yeah?
Can you encode the global structure of the gauge group in?
Yes, there's also a generalization, a global picture from that. Mm-hmm. I just want to work locally because things get very complicated otherwise, right? Gluing these things together is not that easy, but in principle it's doable. Yeah. Okay, that's of course nice because we get our gauge structure, but it's flat. So Chern-Simons theory, so we could do, but nothing else. So let's look at an improved version. Extend our Chevalier-Eilenberg algebra, so the algebra of functions on this grade-shifted Lie algebra to something called the Weil algebra. So what's the Weil algebra? The Weil algebra is nothing but the grade-shifted tangent bundle of our grade-shifted vector space underlying the Lie algebra. So we have now two copies of this Lie algebra around. And on this vector space, there's a very natural vector field, or on the algebra of functions, there's a very natural differential. Namely, there's this shift isomorphism on coordinate functions, and I can use that to extend the usual Chevalier-Eilenberg differential, which gives me the structure constant. That was our usual Q on the Lie algebra. I just add the sigma to it, right? And then I respect this calculational rule. Sigma is of degree 1, so it should anti-commute with the QCE. That fully defines actually the Q on the Weil algebra. Okay? Don't worry too much about the details. There's a trivial extension of the Chevalier-Eilenberg algebra to this Weil algebra. And now the morphism of differential graded algebra gives us precisely what we want. Namely, the coordinates of degree 1 will be mapped to gauge potentials. The shifted coordinates, which are the coordinates on the second copy that we have around, are now mapped to a 2 form. Compatibility with Q, with the homological vector field Q, imposes this relation. So the 2 form is indeed the curvature of A. And moreover, compatibility of Q with on the shifted coordinates gives us the Bianchi identity. Right? So just from morphism of Weil algebra of my Lie algebra to the differential forms, which, by the way, can be interpreted as the Weil algebra of the manifold, gives me all the kinematical data of my gauge theory. I get the gauge potentials, I get the curvatures, I get the Bianchi identities, and gauge transformations follow straightforwardly from homotopies. So the full information about of the kinematical data of a gauge theory is encoded in such a morphism. And this is now very powerful because I can replace things, right? Instead of having here the Weil algebra of a Lie algebra, I just put a Weil algebra of an L-infinity algebra, of an L-infinity algebroid. Instead of having differential forms here, I put something else, differential forms on a categorified space, on non-commutative space, on anything else that you want, right? And this automatically, this formalism tells you what is a gauge theory in this context. You choose a symmetry structure, you choose a structure of one form, so to speak, or differential forms, and this formalism tells you what the gauge structure is, okay? What the corresponding gauge theory is at a kinematical level. No dynamics, of course, right? And the complete picture, I should say, has been developed by Hisham and by Schreiber and Jim Stashev in 2008. So there's a complete picture. Let me not go into details because I'll certainly be running out of time. The original idea is by Cartan, has been rediscovered then by various people, Dauria, Frey in the context of supergravity, then Strobel and so on have done these Poisson sigma models, and then but the full nice picture where everything is clear has been done then in 2008. So here's the Chevalier-Eilenberg algebra, here's the Weil algebra that gives us our connection and curvatures. And the only thing that I want to stress, because I need to explain that a little bit detailed, is that there's a sub-differential graded algebra in here, and the morphisms that are induced there correspond to the topological invariance of your gauge field theory, right? So this structure encodes not only the kinematical data, but also the topological invariance. And this is now the source of a little bit of headache, as I'll explain in the following. Headache. Okay. So, so there are many other equivalent ways of getting precisely the same picture. You can start from L-infinity algebras. They come with something very nice that everybody working in string field theory is familiar with, the homotopy Mauer-Cartan equations. You can use them to construct precisely this same picture in a slightly shorter way, probably, and you get the same curvatures as from this morphism of differential graded algebras. You can differentiate the Mauer-Cartan forms on L-infinity algebras. It gives you also the same picture. So this picture is reproduced from many different perspectives, and they all get the same situation. Penrose-Ward transforms that Martin, I think, will talk a little bit about, also give you that pictures of local connection forms, right? So all of them lead to the same thing. Doesn't matter which definition you start from. However, this is an important point, and I think this is a reason for a lot of confusion. This cost me a lot of time because I didn't read Hisham's and Ul's papers in enough detail. This inf G, this thing here, which is responsible for our topological invariance, does not respect these quasi-isomorphisms that I was talking about before, right? So you have L-infinity algebras, and equivalent L-infinity algebras are related by quasi-isomorphisms, right? And what we would want, of course, is that physics doesn't care which quasi-isomorphic version of our L-infinity algebra we choose. However, this inf G here, as it's constructed, as I constructed the Weil algebra and the inf G, does not respect these quasi-isomorphisms. This is fine if you want to define higher Chern-Simons theory because your curvatures are zero anyway, you don't care about this. However, if you want to do something like the 1-0, 2-0 theories or self-dual strings or something like this, where you want higher gauge theories with non-trivial curvatures, this is a problem because your curvatures will be non-zero and you do care about this inf G, actually, about the topological invariance. You have non-trivial topological invariance. Now, there's an alternative and a way out. There's a simple modification of W of G that you have to perform so that this quasi-isomorphisms are now respected for a certain class. And this leads you to string structures, which are the equivalent of spin structures on loop space, right? So there's a very nice picture behind that. This is actually a subtle point, though, and my conclusion so far is that just while Chern-Simons theories and Yang-Mills theories are the same for Lie algebras, they have the same kinematical data, there's no difference. It seems that the higher analogs somehow split off that there are two ways, right? You can define the kinematical data for higher Chern-Simons theory, that's one way, and the kinematical data for analogs of Yang-Mills, also 1-0, 2-0 theories, and they'll have slightly different kinematical data, and you have to modify that. And I think that's a lot of the source of dismissal of higher non-abelian bundles, because if you start playing with these non-abelian bundles, it's very hard to get non-trivial examples. And a lot of people, physicists, tried that and played with that, and they concluded there's only abelian stuff behind that. And I think this is precisely the point. You have to do this modification. Otherwise, you'll end up with abelian stuff very, very quickly.
Can you say one more word? What does it mean? Does it modify in some sense your definition of
It modifies the definition of curvatures and the definition of gauge transform. It modifies the definitions of curvatures and modifies the gauge transformations.
Which means that your notion of what a topological invariant is changes?
No, that stays the same, but it's now invariant under categorical equivalence, right? So if I go from one L-infinity algebra to a quasi-isomorphic one, that's okay. The topological invariance, they also form, these things also form differential graded algebras, so they're dual to L-infinity algebras, and these L-infinity algebras will be again quasi-isomorphic now. So that they do exactly what you would want. But you need to do this twist. If you don't do that, then all hell breaks loose. You can't write an interesting dynamical principle because gauge transformations will keep you from things and so on. So it really only works for higher Chern-Simons. So my conclusion at this point is you really need to do that. Kind of the definition of gauge theory splits off. You have this higher Chern-Simons, that's fine. You can do that, string field theory and so on. But for the 1-0, 2-0 theories or so, if you want some non-trivial curvatures, you need to modify things. And I struggle a lot with this point, and I would have loved if somebody had pointed this out to me earlier, so I make a point of stressing that. Okay, so higher gauge theory and M5 brains. Okay, so I'll tell you now a little bit about M5 brains. That's, of course, the ultimate aim. However, this is a hard problem. It's not so much hard for a lot of the arguments that are around. Well, possibly people just see further than I do with these arguments, but it is a tough problem to crack. But why not? I mean, well, it's useful to use these techniques to try to solve a problem, and yeah, take everything with a grain of salt, of course. Yeah. Okay, so why M5 brains and higher gauge theory? Very naive picture, but that motivates essentially the essence behind it. D-branes interact via strings. Effective description is the theory of the endpoints, namely the gauge theories in the world volume of these D-branes. Paratransport is gauge theory, and we can learn a lot about string theory just by studying gauge theory. I think everybody agrees with these statements. M5 branes interact via M2 branes. The effective description is a theory of self-dual strings, namely the boundary of the M2 branes is no longer a point, but it's now a one-dimensional object. And the paratransport of these gives rise to a high gauge theory. And now the question is a long-sought 2-0 theory a high gauge theory? There's quite a lot of evidence for this. Question is whether it's a classical, so whether it makes sense to use classical structures to describe it. But let's see how far we can get, right? I mean, let's push this a little bit. Why not? Prehistory, yeah, I'll be reasonably fast with this. You know, conformal quantum field theories are particularly interesting and important. Everybody agrees with this. The conformal algebras and their supersymmetric extensions have been classified by Nahm in 1978. Most people believe that they're only interesting examples for dimension less equal 4, but then Witten came along in 1995 and constructed a superconformal field theory in 6 dimensions, or argued that there is actually such a thing because of string theory reasoning, type 2b on R15 cross K3. And there you get these self-dual strings. But of course, you get them also in M theory, and that was argued then shortly later in 95, 96. So what do you get? You have these self-dual strings. They are boundaries of the M2 branes between the M5 branes. They become massless if the M5 branes approach each other, right? So if they're separate, they have mass. If they approach each other, if they're on top of each other, they become massless. And yeah, so it should give you a description of stacks of parallel M5 branes. The field content is quite obvious because Nahm classified also the representation of this 2-0 superconformal algebra. We have a self-dual 3-form field strength with a 2-form potential. We have 5 Goldstone scalars. They just parameterize the symmetry breaking. If you put a 6-dimensional M5 brane in flat space, right, you have 5 transverse directions, and these are the Goldstone scalars for this one, for breaking of the symmetry. And you have fermionic partners. The observables has been argued many times that there should be Wilson surfaces instead of Wilson lines. So that points towards a higher gauge theory, parallel transport of strings, right? And the common held belief is that there's no Lagrangian description. It should be as important as n equals 4 Superyang-Mills for string theory, so it's very, very important for understanding dualities to get a good handle on this. So huge interest in string theory and also in the mathematics community. I don't have.
Sorry, when you say that, I'm slightly confused. I mean, there are Wilson surface observables, but there are also local operators.
Sure, you get other observables as well. But to get Wilson surfaces, I mean, I'm collecting just hints for higher gauge theory, right? So if you have a Wilson surface, then you want higher.
Those, among the list of observables, there are.
Sure, of course, yeah, exactly. Okay, so that would be a wish list. And I find it a little bit disappointing that nobody explicitly wrote this down. I think to the people working on this, everybody knows these, but me starting on this and not having too much idea of 2-0 theory, I had to compile this myself. So if you have further points, I'm very, very happy if you help me expand this list. So what do we want? A successful M5 brane model should have the following properties. We want an interacting self-dual 2-form gauge potential. It should be based on sound mathematical foundations. That means we want to be able to put it on arbitrary manifolds, right? We don't want to do a naive construction by hand where we introduce structure constants here and there and see what comes out. We want something that's mathematically consistent from the outset, right? And we have higher bundles, so let's use them. Field content of the 2-0 theory should be in there. It should be at least n equals 1, 0 supersymmetric. The reason why we accept slightly less supersymmetry in a manifest formulation is because M2 brane models have a similar feature. They only give you n equals 6 instead of n equals 8, right? So that's reasonable to expect. The gauge structure should be natural and should match some expectations, so there should be relation to ADE gauge groups and so on. We want non-trivial couplings and an interacting field theory, of course, otherwise this would be pretty boring. We want restrictions to the free 2-0 tensor multiplet. We want a non-abelian self-dual string. That's like the M theory analog of a monopole, right? Like you have in 4-dimensional Superyang-Mills theory, monopoles as BPS state. Here you want the self-dual string as a BPS state. We want reductions to 4-dimensional Superyang-Mills. and ideally also 5 dimensions. I have no idea how to do 5 dimensions, so 4 dimensions kind of works, or well, at least there's one limit in which it's contained. And ideally also 3-dimensional Chern-Simons meta-models. There's no reason from M theory to expect that, but it would be nice to have that, so that's more a wish list kind of feature. That's a very, very tough challenge to explain S-duality after reduction to 4 dimensions, and to expect match the expected moduli space of the 2-0 theory. And there's a couple of other things that are quite hard to attack. But if you have a favorite point that's not on this list, just let me know. I'm always happy to extend this list. And it's very important, I think, that this is collected once so that we know what our goal is. Yeah?
If you've got a self-dual string as an RPPS solution, you should also
Show off the other one, yeah. Yeah, exactly. I know. It will be included from now on. So that was the first extension. Okay, arguments again. So why do people believe that there's no such thing as a classical M5 brane model? The first objection is a rather old one. It's just as a non-abelian parallel transport of strings is quite problematic. So let's imagine that we have here our 2 endpoints of the self-dual string, or of our string, and then we subdivide it in 2 halves, and we want to parallel transport it to the bottom string that we also subdivided in 2 halves. There's now 2 ways of doing that. First, I can transport the first half all the way to the bottom, and then the second half all the way to the bottom. Or I transport both of these to the middle one, and then to the bottom one. Okay, so there are these 2 ways of transporting it. And of course, it should be the same, right? It should be consistent, and so therefore these should be the same. And now if you assume that these are just groups, then you get this equation. And this is a very old equation that has been studied by Ekman and Hilton in '62, and it just tells you that this group G has to be abelian, right? And this has been rediscovered quite a few times by physicists in the 80s and 90s, that if you have such a parallel transport, then the parallel transport should be abelian. Now, what's the way out? Well, the way out is to use 2 categories, and therefore high gauge theory, because in 2-category theory, we have 2 operations, namely that's vertical composition and horizontal composition, and it automatically satisfies the corresponding equation just from the axioms of 2 categories. So if you develop 2 categories formulated axiomatically, you get this equation. It's known as the interchange law, and it's precisely that this parallel transport is consistent, right? So it's all good. We just have to use 2 categories, right? I mean, just using groups is too naive. You have to go to a high gauge theory. The second objection is a very physics objection, and it's a very interesting one, important one. It says, well, our 2-0 theory was a theory at conformal fixed points. Therefore, we don't have a dimensional full parameter, right? It's a conformal field theory. We don't have dimensional full parameters. The fixed points are the singularities of K3 surfaces, singularities in moduli space of K3 surfaces. So they're isolated. So we don't have dimensionless parameters. So we don't have parameters. There should be no classical limits, so no Lagrangian. That's a standard string theory folklore, and that's what most people will tell you if you talk to them about this. Actually, this has been proven rigorously. So in 1999, then Beccard, Henno, Severin looked at BV formulation of self-dual 3 forms and looked at the continuous deformation of the BV complex, and there are no continuous deformation of that. So we know that there's no continuous deformation away from the abelian theory to something interacting, right?
That wouldn't be the theorem that I would say. I would say Cordova, Dumitrescu, and Trilogator, who proved that with 1-0 or 2-0 superconformal symmetry, there are no relevant or marginal supersymmetry preserving deformations.
Yes,
but they just proved from the superconformal algebra.
Yeah, but don't you have to look at the quantum dimensions of these?
It's got nothing to do with. It's a pure statement about the superconformal algebra.
Okay.
Of the full quantum theory.
Ah, okay, right. Oh, okay, right.
There's no other input than the fact that the theory is superconformal invariant.
Okay. So you can just see it from there that you don't have continuous deformation.
No, so there are no relevant deformations, no marginal deformations.
Okay, right. Exactly, yeah. This is what you would expect, yeah. I mean, this is the proof that I know from BV, right? It's just you don't even need the
super. This has got nothing to do with the free theory.
Okay.
The theorem of Cordova and all has nothing to do with.
Sure. Yeah, but you could argue, well, the superconformal algebra is probably too general. Probably I get something that's not. I don't know, not super. I don't even want to use supersymmetry, right? This doesn't even use supersymmetry. It just tells you if you have the abelian theory, you just try to deform away from it. You don't.
I'm saying it's a much more powerful
Okay,
theory.
right. Okay, so we know that there are no continuous parameters. We can agree on this, right? And well, you can answer to this that actually the same happened for the M2 branes. And there you get integer parameters because it's a Chern-Simons matter theory, so the coupling constant is quantized. And there they arose from geometry, so there might be some hope to get something similar there. And indeed,
3 dimensions, so that's what's different. In 3
Yeah.
dimensions, there are non-trivial RG flows
Mhm.
between theories. So you can flow from a Lagrangian field theory, some supersymmetric Yang-Mills theory, to an infrared fixed point,
Right.
which is the superconformal field theory on
Mhm.
Supergravity. That's what Cordova et al. Showed cannot happen in.
Well, but the flow implies that I have a continuous set of parameters,
The
right?
flow is just the RG flow.
Yeah, sure, but it means it's continuous, right? I would need a continuous parameter. I don't have that anyway, so I know that there's no flow.
There are marginal parameters in the supersymmetric Yang-Mills theory, but there is an RG flow to a fixed point theory. I'm talking about relevant deformations, not
Right.
marginal.
Ah, okay, right.
Irrelevant deformations either.
Right.
What about irrelevant?
Irrelevant, they're lost.
Mhm.
No,
But they're no relevant or
Right,
marginal.
but
Okay.
relevant, like you said, you are interested in irrelevant because you are interested in UV fixed point, not IR fixed point.
No, I know, but what happens here is the bottom of this slide has to do with an IR fixed point. So there's a Lagrangian field theory that flows.
No, but RA by metric it doesn't flow, it just goes through.
No.
It's
I'm-
We can talk about
Okay. Yeah. So anyway, the fact. So just the simple argument that at least I've read in lots of papers that there's no continuous parameter is not directly a source for a reason to worry too much about this, because we saw the same happen in M2 brains. There might be further arguments that are important. Then there's a common objection that the dimension reduction is unclear, and indeed I have no idea how to reduce to 5-dimensional Supergravity. 4-dimensional seems somehow to be encoded in that. I agree that what I'll show you is probably not the nicest thing, but it seems to be contained. Okay?
Sorry, Chris, can you go back? Why do you say dimensional reduction is unclear when you just say I put the thing on a circle?
No, it's clear what should happen, but the dimension reduction for classical Lagrangian. This argument that if I reduce in one way, I get 1 over r d5x. If I reduce in another way, I get d5x. So that's one of Witten's standard arguments, right, against the existence of a classical Lagrangian. If I reduce in one way, let's go through this. If I reduce on a circle, right, then radius r yields a volume form, so I should get something like this, okay? On the other hand, conformal invariance for the F-wedge-Hodge F term in 5 dimensions requires a volume form like this, and this is clearly a contradiction.
F-wedge star F is not conformal.
Yeah, well, if I have a 1 over r d5x volume form.
on dimensional grounds.
Yeah.
Yang-Mills.
This is just this dimensional argument, yeah, exactly. Yeah. That's just it. So no idea how this works. Right. Okay, so let me show you our attempt so far. And yeah, this is very important, right? So what can we do? The first question that you would ask is, what is the higher group that you should be using for this theory, right? I mean, if I look at Yang-Mills theory on D-branes, it's pretty clear. Well, if I have flat D-branes, I know that by these usual arguments, I probably want UN. If I have complicated geometries, I get other groups. So what should I use here? Because I have these two freedoms. Now, if I take a Lie-2 algebra, I need to specify 2 vector space. So I have a lot of freedom, actually, right? And I should somehow get this under control and fix that. And guidance, you can find some guidance, but at least aesthetical guidance from the BPS self-dual string. And let me remind you that this is a categorification of this string theory, the M theory lift of this string theory configuration. So you have a D1 brane ending on D3 branes in this manner. And from the perspective of D3 branes, this just looks like a monopole. So there's a BPS configuration, and they get the Bogomolny monopole equations in R3. If you lift this up to M theory, you have M2 brane ending like this. It's now flat, right? So apologies for this picture with this little wiggle in there. It's really this flat configuration. And then you get the self-dual string with this higher form of the monopole equation, right? I just write the abelian part because that's the uncontroversial stuff. Okay, so now let's try to rephrase that all mathematically properly. So what happens in the monopole case if you go from the abelian case to the non-abelian case? Well, I have the Dirac monopole, and I want to go to the Topf-Polyakov monopole. So the Dirac monopole, remember, that means that I have one point in, if I have a single monopole in R3, where I don't have a gauge potential. So ideally, I describe it by a sphere around this point and a principal bundle on top of the sphere. The principal bundle that belongs to that is just a Hopf vibration. So you have a U1 fiber bundle over S2, and the total space is S3. And now in going to the global picture, to keep the topological information there, I should keep the S3. But on the other hand, I want to expand it. So the difference is that the abelian monopole is not defined on all of R3. I have to take out points, while the non-abelian monopole can be extended to all of R3, right? I have non-abelian solutions on all of R3, and that's kind of the characteristic difference that I want to use here. And what you do is you observe that S3, the total space of the principal fiber bundle responsible for the Dirac monopole, happens to be the group SU2. And you take this group SU2, you make it to your gauge group, and then you consider the trivial SU2 bundle over S2, but there's now a bundle morphism. You specify an embedding of U1 into SU2, and then you have this bundle morphism over here. And this is indeed how asymptotically the Toft-Polyakov monopole looks like, right? So that's indeed what's behind that. Okay, so if you had no idea what interesting gauge group to choose, you might be led from this picture to say, okay, let's choose SU2 because I can trivialize my monopole, and that might be interesting. And the advantage of this picture is that I can easily lift this up to higher gauge theory. Now let's look at the self-dual string. So H equals Hodge d phi in the abelian case. We're now in R4 in 4 dimensions. A 3 form is Hodge d phi 1 form, right? So again, we can look at the self-dual string in these 4 dimensions just as a point. The dimension in which the self-dual string extends is outside of this picture. It's the 5th dimension, right, that we don't care about. We don't care about solutions fluctuating in this direction. So we have a 4-dimensional picture. And just as the Dirac monopole was a principal fiber bundle over S2, now we can enclose this point where the self-dual string sits by an S3. And there's now a gerb over this. And it's a fundamental gerb. And indeed, for the abelian self-dual string, this is just this picture. We have a fundamental gerb sitting over S3. I wrote it here trivially as a category. Don't worry about this. It just sits over S3. And the group is just BU1, a categorified analog of U1. And now the question is, well, if I mimic the same story as before, so before the key observation was that SU2 had a group structure, or S3, the total space of the bundle, had also a group structure, I can do the same here. So the total space of this gerb, which is a categorified space, a groupoid, Lie groupoid, has a group structure, namely it's the string 2 group, right? So this picture suggests we want as our gauge structure the string 2 group. And there are many, many other reasons for doing this as well. There's only one reason that's nice and geometrical, but there are many, many other reasons. No matter how you approach this problem, a lot points to using the string 2 group. Yeah, so string 2 group and M theory there's many reasons and a long story. It's kind of the categorical analog of spin 3 of SU2, and this is the first group that you look at if you want some interesting non-abelian features, right? And therefore this is justified. You can Lie differentiate this string 2 group, and we've done that actually, and the result is the so-called string Lie 2 algebra. It's very, very simple. It's just Lie algebra SU2 and a copy of R shifted in degree 1. The homological vector field looks like this, or in bracket notation, you have a binary bracket, which is just a Lie bracket, and you have a ternary bracket, which is just a Cartan killing form, right? So you have the commutator here and the killing metric closing this off. Important for this is that there's an equivalent description of this L-infinity algebra, or this Lie 2 algebra, which looks like this. You have the based path space in SU2 and the based loop space in SU2 centrally extended to Kac-Moody algebra. Right? Just a remark, we can do that, of course, for any ADA Lie algebras. Just the only thing that you need is a metric, right? So whenever you have a metric on Lie algebra, you can construct this thing. And also we can twist the Weil algebra for this thing by invariant polynomials to get really the structure that we want, right? Remember that there was this thing between Chern-Simons theories, higher Chern-Simons theories, and 1-0-2-0 theories with non-trivial curvatures that we somehow need to modify the Weil algebra a little bit. And this can be done for this case in a nice way. Okay, so Chevalier-Eilenberg algebra for the string Lie 2 algebra looks like this. You can double it to the Weil algebra, which looks like this, right? And then you just derive the potentials, curvatures, Bianchi identities for our gauge theory. Psi alpha gets mapped to 1-form potential. B gets mapped to 2-form potential. That's good because we want 3-form curvatures around, right? The shifted one, this tells you the curvature for A looks like this. Or, well, part of the curvature looks like this. And the curvature for B looks like this. And the Bianchi identities are these and these. And gauge transformations and topological invariants are then derived as before. And now we need to just introduce this little twist, and it just modifies the definition of the curvature to this one. So something very nice happens. Before we only had this term, and now we indeed have the full Chern-Simons term. Okay, so what's the kinematical data of our theory? We have 1 form with values in Lie algebra, taking values in Lie algebra G, and we just have an abelian 2 form. That's it. Okay, And then you can add by hand also a Higgs field. And then you can already describe a dynamical principle, namely the non-abelian generalization of the self-true string. So this is the abelian one. And we can also just take this as equation for the non-abelian one. And then you get this equation. And then in addition, you get self-duality for this two-form curvature. Right? So indeed, you get then a non-abelian version of self-true string. This also reduces trivially to...
What's that equation mean we're in 6 dimensions, right?
No, this is 4 dimensions. This is a self-dual string in 4 dimensions.
Oh, this is
We are the self-dual string.
In 4 dimensions?
Yes, we just the same thing as you do for the monopole.
String in 6, but it's Hodge styles in 4 because it's on the transverse space.
Yeah, it's only in the 1, 2, 3. Yeah,
The transverse and the...
exactly. Yeah, it's in 1, 2, 3, 4 direction. Yeah, exactly.
Okay.
So you forget about temporal and the extension of the string, and so this is the categorified the M theory analog of a monopole, right? So this is the BPS states that we want to get, right? Okay. So that's what it is, and it reduced to monopoles. It contains the abelian part. And it is actually compatible with categorical equivalence. So this quasi-isomorphism is okay. So you can formulate this exactly as you want. So this satisfies all the criteria that you can throw at it. There's a Bogomolny completion of the action, and this is really the minimum, and so on. It's a little bit disappointing because it's just the instanton and something in the background of the instanton. But, well, this life is what it spits out. And, yeah, so that's just what it is. So conclusion so far. Well, the equation of motion matches the story from 1-0 theory because they also look at exactly such equations. And the higher analog for SU2 is string 3. And these string structures allowed for gauge invariant field equations. That was a big problem because if you don't do this twist, then you don't get this equation gauge invariant way without f being 0. And we don't want f equals 0 because then our configuration is trivial, right? So the twist was very important. And we have really non-abelian, non-trivial higher bundles, right? I mean, this was something that people wanted. So do you have an example, a non-trivial example of a higher non-abelian bundle? Well, the one underlying this, the string structures, are actually there. And as I said, it's agnostic about quasi-isomorphism, so you can also write the same thing down for quasi-isomorphic L-infinity algebras if you want. Okay, now about actions of the 6-dimensional superconformal field theory. So how do you do that? Well, I mean, deriving supersymmetric actions is a lot of hard work. So first thing you do, you look in the literature and see what other people have done. And there's this nice model that was derived from tensor hierarchies in gauge supergravity by Sample, Msetsky, and Wimmer in 2011. There were a number of issues with this model. So the choice of gauge structure was very unclear. So they just constructed it by hand, trying to close supersymmetry equations, and they found a gauge structure. But it was not clear which ones to choose and if there's non-trivial examples. They had cubic interactions, they had scalar fields with wrong sign kinetic terms. Self-duality has to be informed by hand. And it's not clear how this wish list had to be informed. This was really constructed by hand, the usual way that you have lots of structure constants somewhere and they make them close. You get relations on structure constants. But then the mathematical structure was not clear behind that. Right? So what we showed already previously is that this extra structure, or this gauge structure, is essentially a categorified Lie algebra with some extra structure. Right? And now if you look at this with the idea of using the string Lie2 algebra that we used previously for the self-dual string, then this is indeed an appropriate gauge structure for this model. There's one problem, namely we need a suitable notion of inner product for writing down an action, right? You need the analog of metric Lie algebra if you want to write down an action. But this is also now clear from the abstract perspective because we know such inner products come from symplectic forms on our NQ manifolds. And as a consequence, we need to extend string G. Don't worry why this is now a Lie3 algebra. I have to skip this detail. We have to extend this now to a symplectic vector space. So you essentially get this one. And you need to extend it one step more so that this is quasi-isomorphic to this thing, which is quasi-isomorphic to the ordinary Lie algebra. Here you get indeed a natural inner product. And this is indeed, if you work out all the details and so on, you can just plug it into their model. This works. It has exactly the structure constants that you work. So this is an appropriate gauge structure for their 1-0 model that they derived in supergravity. Okay, so what does it look like? Field content is you have an abelian 1-0 tensor multiplet, a couple of abelian, 2 actually of these. You have a 1-0 vector multiplet that takes values in G plus R. And you have an additional non-dynamical C field that takes values here. And then you can write down this action. So that's their action just specialized to this case. And it solves 2 problems because we have now a clear idea of what gauge structures we can choose and what they mean mathematically, what the bundle structure is, how to put them on arbitrary manifolds in principle, right? And there's no cubic interaction terms for scalar fields, which might be good news. I'm not sure if that's really that important at the moment, but yeah, let's see. Certainly helps a little bit. Okay, so then you need to complete the theory to the full 1-0 picture. Namely, first of all, you don't want self-duality to be imposed by hand. So there's this Pasti-Sorokin-Tonin type actions. And you can indeed complete that. So Samtleben et al., they already completed it. The bosonic part was PSD completed. Then they announced that they would also do the full action, but it never appeared. According to our calculations, it would be very, very hard to do it in their general setting, right? So I'm not sure if it's even possible in their general setting. However, if you restrict the gauge structure to our string structures, this construction is very possible and it simplifies actually. So you have a nice PST completion of our action.
Do you think PST is essential? I mean,
I don't know.
Some kind of slicing. You need what do you call it?
You get these auxiliary fields, right? So.
Well, you need to have a manifold which you can slice in time.
Yeah, I don't.
Foliation.
Yeah, also, right.
Otherwise, simply impossible.
Sure. I mean, there is a few problems with this PST form. I mean, the idea is here we try to put everything in the action so that in principle you could ask, can I quantize that? Or at least can I set up BV, classical BV to quantize that, all right?
But still quantization.
Yeah, sure, right. Yes. At the moment, it's just, let's see how far we can push the thing. What can we build together? And indeed, you can do this PST thing. So there's something that my PhD student computed. It was very nice computation. It works. So you can do it in principle. PhD. PST student, yeah, that was a good one. Okay, then you also want to add matter fields, of course, to get the full content of the 2-0 theory. So you add hypermultiplets. And they already discussed the general construction, how to extend it superconformally by hypermultiplets. So you make a few concrete choices with this twisted string structure that tells you what to do. And now you get a 1-0 theory in 60 that satisfies, well, let me exclude the many, but it satisfies some of the wish list items. Okay, the controversial stuff that you can already do with this one is you can look at the reduction to 4D superhang Mills and also 3D Schoenstein's matter theory. We show you how this works in principle. It's a very naive construction and there's no good physical motivation for it, but it works to that extent, right? So this is work in progress, right? This is not a finished model. So this is our action, and I marked two terms in red. These are these two. And now if you want to have a 6-dimensional theory that reduces to 4-dimensional superhang Mills with ADE gauge group, you just do the following. Well, you know that you want this 4-dimensional gauge coupling with theta term, which looks like this and relates to the torus parameter like this. You give phi s and you give bs vacuum expectation values. Something similar happens for M2 brane models, but there they have better arguments why you would want these vacuum expectation values and how you choose them. However, you see if you give phi s this vacuum expectation value, if you give bs this vacuum expectation value, here this is already 6-dimensional superhang Mills. With this vacuum expectation value, you integrate over R9, R10. You just get 4-dimensional superhang Mills. This here is just a topological term that's left over then in 4 dimensions if you give bs this vacuum expectation value. And of course, what you have to argue is you say these are R9, R10 are very small, so we perform a strong coupling expansion around these vacuum expectation values. And the only things that you're left with is indeed 4-dimensional n equals 4 superhang Mills with theta term. Right? So it's in there, but I would agree if somebody doesn't like this reduction procedure, it's a little bit ad hoc. Right? The other reduction is the reduction to M2 brane model that you would... Yeah?
I mean, normally when we do these reductions, I was thinking actually about what the resolution is with the 5D thing. The point is, when you go from M theory to string theory, you have to go between 11-dimensional Einstein frame to string frame, which involves rescaling factors of R.
Okay.
And so somehow here where you've got these factors of the volume, that should be related to higher up, going between Einstein frame to string frame, and then
right. Okay.
through by appropriate things, rather than just saying.
Yeah, I'm sure that you might cook up good reasons for that. I'm just not, so don't know enough about the string thing.
Normally, the W bosons of the non-abelian gauge theory in 5 or 4 dimensions arise from strings wrapped around the torus, the short
Sure.
one. All right, and so that's why things work the way they do. Here, he's getting them directly from degrees of freedom of a super-Yang-Mills theory in 6 dimensions.
Yeah.
So that it is not the way it's conventionally supposed to rise. And moreover, now you're worried that there's double counting, because you'll get things that look like W bosons from the wrapped strings, and things that look like W bosons from this Kaluza-Klein reduction.
Sure. Yeah, I mean, I should stress that I think that what we have here is, so to speak, well, at least from what we see, is that should be considered as the additional non-abelian contribution. What has been split off is the center of mass motion, where the usual reduction happens. So in that sense, well, there might be issues with this. I mean, what this looks like is a little bit like these Hanani-Zaffaroni models, where you have NS5 D8s and D6s and so on. And
in general, you can't separate them. Right? We know in equal 2 and 4 dimensions that you can't really separate the matter.
No, the way you usually do it is you go out on the Coulomb branch, right, where the gauge symmetry is broken to the Cartan, right? And the Cartan generators directly come from reducing the B field. Those become Helian gauge fields in the lower dimensional theory. And the W bosons, because those are BPS particles out on the Coulomb branch, those come from the wrapped string.
Yes.
Right? That's the usual picture.
Yeah, for the abelian.
Here we have a super Yang-Mills in 6 dimensions that he claims directly produces both the Cartan generators and the W bosons that go along with them. So that's a very different picture of how these.
I mean, if once you go to the Coulomb branch and everything is broken to U1s, right? I would claim that these degrees of freedom are not in this model, that you add them by hand. So this is only the kind of the non-abelian part. So this should be the part that completes your U1s again to
No, but I
U2.
said what usually completes the U1s is the wrapped strings. That's the point.
Okay. Yeah, I should definitely talk some more about this. Yeah. Yeah.
How is the S duality supposed to work?
Yeah, that's no idea. Don't know.
So what is, I mean, when you reduce, so what is?
I mean, you would somehow expect that that phi s and bs are rotated into each other, right?
I mean, normally it works because you've got the SL2 action on torque.
Exactly, yeah.
The torque is then the complex modulus of the torus.
So this is like
That's why I'm confused by your
The wrapped strings, when you have a torus, right, you have
Sure.
electrically and magnetically charged wrapped strings. And so normally the electrically charged guys are the W bosons and the magnetically charged guys are monopoles. And they get exchanged under this duality.
Sure.
Under SL2.
Yeah, in this sense, it would map these two vacuum expectation values into. But it doesn't look manifestly as duality invariant or anything like this at all, right? So this looks like it has chosen somehow a preferred frame or something like this.
Extra stuff that you have on that somehow disappears.
Yeah, all the other stuff goes away. Yeah, it's just this stuff that you're left with. There's two phis in the game. There's a phi s. It's just from the gauge structure. There's one phi r and a phi s, and the phi r is essentially can be gauged away, and the phi s is the distance between the M5 branes.
So that which is R2 value.
Yeah, exactly. This is why there's R2 value. One of these R2 value factors is just gauge, and the other one is same supermultiplied as the phi that parameterizes the distance between the M5s, right? So you see that the center of mass motion is gone, right? The center of mass motion you would have to put on top of that, right? So there's an additional U1. Yes, exactly. Yeah, precisely. Yeah. Yeah. Okay, so yeah, let me talk about these things that work, right? That more obvious. So something nice that works also is the reduction to M2 brane model. So what you can do is you can replace the R15 by R12 cross S3 or any compact 3-dimensional manifold for that. You take the string Lie 2 algebra of SUN cross SUN. You suppose that's trivial on this internal space, which is assumed small, but you expect it to be non-trivial on this R12. And you demand that the B field is turned off on the R12, but it encodes an abelian gerb of Dixit-Meduadi class. That's the characteristic class of the gerb. The topological class on S3 is just K. And now, because the 3-form curvature is dB plus CSA, you have this H wedge, Hodge H term in there. If you now integrate over the S3, then it gives you from the gerb, you get K times the volume factor times Chern-Simons of A. So this thing here reduces to integer times Chern-Simons, and in this way you recover the Chern-Simons meta theories of ABGM type. I mean, you have to look at the other terms as well, but I mean, this is the easiest term to understand. Okay, reality check now to all the stuff that doesn't work, right? So, but I'd like to keep this quote in mind, right? It's not all bad, and in particular this, right? So we are still putting up a fight. We don't give up yet. Our model is most certainly not the desired 2-0 theory, and clear pointers are that the free Yang-Mills multiplet contradicts 2-0 supersymmetry. The modular space of vacuum is not that of multiple M5 branes. We don't know how S duality works. The PST mechanism relies on phi S being larger than 0. Phi S equals 0 is exactly when the M5 branes are on top of each other. So there we see that the 2-0 theory is most likely hard. The scalar field has a wrong sign kinetic term. I think this can be fixed, I'm pretty sure by now. Model is not compatible, and this is actually interesting, not compatible with categorical equivalence. So if I go with their action that they derived from tensor hierarchies, and I choose a quasi-isomorphic string structure, or formulation of my string structure, this doesn't work in their model. It works for the self-dual string that we wrote down. So we strongly believe that physics doesn't see quasi-isomorphism, but here it doesn't work, okay? And now we turn this problem into a hint of a solution. So this model is not categorically equivalent, so there's a problem in this model, and we know even where this problem appears. So if you know gauge these tensor hierarchies, they have this embedding tensor, and in supergravity what you always do, you split this embedding tensor into antisymmetric part and symmetric part, and you say the antisymmetric part gives my Lie algebra structure constant, symmetric part gives me some additional maps there, some representation maps, and this splitting is too rigid. You can't actually do that in the general context. In the general context, you have to take part of this antisymmetric map also into this D. Okay, so the next step, and this is work in progress, unfortunately still, it's not that easy. So we need Lie 2 algebras with the right branching. So just as you can branch UN into factors of U1 and smaller UNs, you would work the same to do with string 2 algebras, but this is actually hard to find examples. What we're working currently on is the correct formulation of this in categorical equivalence invariant way. So we want metric twisted Weil algebras and categorical equivalence. That should come out hopefully in January. So we have a much better understanding now of how these twists work and what you should really do in the metric case. And once you have that, once we have a clean setup for our higher bundles, then we can rederive the sum-lim action from first principles, just postulate supersymmetry transformations, derive the action in a correct way to get really at least a theory that's classically, mathematically at least perfect in a sense. And yeah, I mean, I've finished 5 minutes early, but I think nobody will regret that. So summary, higher gauge theory, classically at least, might underlie M theory. What I hope I showed you is that the classical analog of SU2, the higher analog is actually string 3, so the string structure that we had, string groups. There is a non-abelian self-dual string. You can write something down. It fulfills the things that you want. There is a classical action with many of the desired feature. However, it's clearly not the 2-0 theory, right? So what we need to do is we need to understand the generalization of these string structures, and this is certainly work in progress. We need to understand categorical equivalence, because that's very important that our theory is mathematically consistent, right? We start more from the mathematical side. We want that everything there is under control and consistent before we start to construct supersymmetric actions. What we want to study is a little bit more the 1-0 models. So I have a student looking at this Hanani-Zaffaroni configuration and try to make sense of them or apply this action there. And then there's various links, various things that you want to study afterwards. Categorified integrability, Penrose-Ward transforms. Martin will talk a little bit about this. Higher quantization, because it also appears in the self-dual string picture. Fuzzy S3, how do you quantize with respect to 3 forms instead of symplectic 2 forms? And hopefully we get some better understanding of M theory. Okay, and then shameless further advertisement, not only of higher structures, but also I got a grant, and there's a postdoc 3 years and a PhD position 3.5 years. If you're interested, contact me. I'll be very happy to consider your application. Thank you very much.
Thank you, Christian, for a very nice lecture, which touches on many topics that we will hear in the next few days. So are there any questions for him? Joseph?
So you said, okay, you don't have 2, 0 supersymmetry in this case. So
yeah.
Normally super Yang-Mills and 6D have 1, 1.
Yeah.
So but you don't have 1, 1 either?
I have 1, 0. Right, it's the chiral Yang-Mills.
So when you reduce to 4D though, you end up with 16 supersymmetry. So
because I also added the hypermultiplet. Right, so I have 1, 0. The 1, 0, 1, 1 multiplet in 6 dimension is a 1, 0 vector plus a 0, 1 hyper, right? So I added the hyper by hand. that was probably not clear. When I said I complete the theory, then I said that I also added this one. I mean, the fact that this free Young-Mills is around is precisely here.
So you added the 60 hyper?
The 60 hyper, yeah.
So that theory then has still 1,0.
It still has 1,0, yeah. But it has the matter content for the right matter content.
Jacques?
So I had a couple, maybe you could put the slide with the action back.
Yeah. This one probably, yeah.
Yeah, I guess that's the one. So a couple of things. So first of all, if you're really after the 2-0 theory, one of the things is that it's only defined for simply laced G, whereas this thing looks
Any metric.
perfectly fine for any G.
Yeah.
And the second question is about anomalies. Typically, if I have just a super Yang-Mills multiplet for some arbitrary G, and the rest of the matter content that you wrote down, I'm gonna. That's not that's a theory with anomalies.
Right. You have to be careful in what combination you have. Yeah.
So, in fact, since you didn't add any matter that was charged under the gauge theory, if I understand.
No, it's charged. These additional hypermultiplets will be charged.
Those are charged under the gauge
Yeah,
theory?
exactly. Yes, of course.
Oh, I'm sorry. So that's not completing the 1-0 tensor multiplet to the 2-0.
No. It's just the same field content, so the same number of scalar fields and so on, right? But it's not. It's by no means the 2-0.
What representation of the gauge group do you choose?
This is just fundamental, yeah. Oh no! Wait. It should be adjoint, yeah. It's adjoint.
The adjoint of the gauge group.
Yeah, I mean, it's adjoint.
So that's, as Joe said, very far from the matter content of the 2-0 theory.
Sure. Yeah. I mean, you have the right number of scalar fields.
No,
and so on.
well, for arbitrary G, no.
Yes, that's sorry. No, sorry. These are in the fundamental. They're not in the adjoint. They're in the fundamental representation. Yeah.
Well, you tell me. But fundamental representation for arbitrary G?
Yes.
Just for G equals SU2?
Well, for this you can write down for any action. But would you?
I know. That's why I'm very confused.
Yes. But would you?
Almost every action you would write down with hypermultiplets and representation R and gauge group G. Just anything you write, most things you write down are anomalies, right? Only for very special choices
Yes.
will the anomalies be cancelable.
Yeah.
And even then, you probably need some Green-Schwarz mechanism to do it.
Yes.
And so.
But you would. This is also not classical, right? I mean, would you expect that to see ADE restriction to see that at a classical level? I don't think so, right?
I'm not sure what I'm supposed to expect.
Yeah, exactly. But I don't think you would expect to see that at a classical level. And the same with the anomalies, right? I mean, I can't quantize. This theory is not unitary as it stands, right? So I can't quantize that anyway.
So what kind of anomalies are we worried about? Because each kind of anomaly is already.
Just gauge anomalies. The theory has gauge anomalies up the wazoo for arbitrary G and representation R in the hypermodel. Right?
Yeah, with respect to this kind of higher gauge group.
With respect to the ordinary, zero-form gauge symmetry. I mean, a higher gauge, higher anomalies in the higher symmetries are also possible, but just with respect to the ordinary zero-form gauge symmetry, this will typically be an anomalous there.
Yeah.
I mean, the Green-Schwarz mechanism can be understood also in terms of higher categorical theory.
So if the anomaly factorizes, then he has a tensor multiplet that he can use to cancel the anomaly. For SU2, maybe you squeak by with that because there's.
I think you do. Yeah.
Whether it's quartic Casimir. But I'm a little bit hard pressed, for other choices of G to imagine that this is not an anomaly.
Yeah, I mean, for other choices of then SU2, it's anyway not clear what you would expect and how many additional things. I mean, this is classical theory. I don't know. Your concerns are absolutely valid. But would you expect ADE, this restriction, at a classical level? Probably not, right?
Well, I mean, I didn't expect a classical theory because
No, of course. Yeah, sure.
So
Of course, yeah.
That
Of course,
I don't know how to answer that question.
if somebody said, I have a classical theory, you would probably not expect a restriction to come out of that one, right? It's very hard to see a classical restriction to ADLE outgrowth, right?
I mean, you know, the other thing is there are lots and lots of 1-0 superconformal field theories. And even if this doesn't work out as a candidate for a 2-0 theory, maybe there's something that you can do in the context of 1-0 theory.
Absolutely.
That would be useful. Certainly, there you're allowed to have, you know, 1-0 vector multiplets and tensor multiplets and hypermultiplets of various representations. And one of the restrictions is, in fact, the theory that the gauge anomalies cancel.
Precisely.
It's quite a powerful restriction. And it really restricts your field content rather stringent.
Yeah, I mean, this is why we're looking now at these Hanani-Zaffaroni configurations, right, which are these ones here. And I think for these, the model should work reasonably well. I mean, what I don't understand, if anybody knows more about this, in F-theory, they also have these phi F square terms, right? I mean, this actually, they have in F-theory, they have these terms, right? I don't think they supersymmetrically completed them, but they write down terms like this, right? But what about unitarity and things like that? Because you have an F here, phi, what if phi is negative, right? And nobody seems to be worried about these things. So this is what I don't understand. But
well, the answer to that is that phi lives on, you know, you have to mod out by the file group for, well, I'll say it in the 2-0 context. You have to mod out by the file group for your ADE. Right? So roughly speaking, it lives on a sort of a...
It lives only on R positive, right? Yeah. And that allows also then...
Yeah. Lives on R plus.
Yes, exactly. Yeah, this is what I would think.
So that's your... You're doing SU2. So phi goes to minus phi is a symmetry you mod out by.
Right.
So phi lives on the half line.
Exactly, yeah.
So there's no problem with it being negative.
Precisely, yeah. So then in principle you can also have the phi cube terms and so on. There's no issues with that and so on, right? Exactly.
Any more questions for Christian? So you mentioned...
So in the membrane theory, we work with lower supersymmetry, but then we think of things like monopole operators that augment the supersymmetry.
Yeah.
Can you think of how to go to 2,0 by including things like the monopole?
Yeah, you have the self-dual strings. You have self-dual string operators. I mean, that's a direct analog, really, of this monopole.
Don't just say the self-dual string operator. With the monopole operators, we can write down what they are and then show that there's a supersymmetry. Can you do anything like that?
We haven't looked at this, but I would expect that you can lift this up because they are really straightforward analogs of this monopole. So you just add one dimension essentially. So I can't imagine why that should go wrong.
I'm always worried when the difference between field theory and the string theory is you just add one dimension.
No.
The difference between string theory and membrane theory is you just add one dimension.
Yes, sure. But here this is really local theory. The only thing that it has. It's even abelian, right? So there's the gerb structure is very, very trivial, and there's not a problem with non-abelian gerbs, right?
I mean,
sure.
Even aside from this thing, I mean, it's very interesting in ABJM if I can get this gate, this supersymmetry realized essentially do not observe effects to really track through something.
I fully agree. So I expect it to work, and hopefully next year with the postdoc and PhD they'll work. Yeah, as soon as I don't have to teach too much, it should be okay. Yeah.
There was this slide where you listed out some issues about, how S-duality comes about. I can't remember.
No, the issues, the wish list, or these problems? No, that was. Could I go in the wrong direction? This wish list? This one, or?
Yeah. So explain S-duality after reduction to 4 dimensions.
Yeah.
So just a small comment. Remember that talk I gave in Durham?
Mm-hmm.
So I'll talk about that tomorrow.
Okay.
Right. Yeah, but there's some new developments.
Okay.
So you can see S-duality being intrinsic in 2,0 theory, without a torus along any direction. So it's almost like type 2b, you have S-duality, but you don't have any torus anywhere, right? But it's a duality of type 2b. So something similar happens in 2.0. And you study that from the ground states of the low string, and we'll see that tomorrow. And likewise with T-duality, you don't have any circles, but you have a T-duality symmetry that's hidden inside the spectrum. So we'll get to see that tomorrow in my talk. I'll explain.
Okay.
Yeah.
Yeah. Cool. Thanks.
Any other questions for Christian? If not, let's thank him again.